So Katherine Richardson is a professor in biological oceanography, at the University of Copenhagen, and she holds several positions in different research institutions in Denmark. And she has also her research, which is really on the biology of the oceans and how they contribute to the regulation of the Earth systems. And one of the important reasons why we invited Katherine today is because she was one of the the lead author of the setup of the Planetary Boundaries framework that has been proposed back in the late 2000s, so 2008, 2009, and which is now quite well documented and used by several organizations around the world to evaluate the state of the planet with respect to the human activity. There was a last paper published this year showing that 6 out of the 9 boundaries are actually transgressed at this state, and it's what Katherine will teach us about, part of what there will be other aspects presented today. And so without further ado, I propose to leave the floor to Katherine. Thank you very much in advance for joining us today. It's a real pleasure.
Thank you for inviting me, David. First of all, let me congratulate you on this whole exercise. I think it's very exciting. I want to congratulate the Dean for letting it happen, the people who have been organizing it, but also all of you that have come. And I know that some of you are really out of your comfort zone and don't really want to be here anyway. But and then there are some of you who think you know it all already, but all of you got a chance to get out of some teaching to do it. So you decided to come anyway. I hope there'll be something in this for all of you. David started by saying that I am a biological oceanographer, and I have a professorship in biological oceanography. That's true. And I have that professorship because I have a PhD in biological oceanography. And as you can see by looking at me, that PhD was attained a very long time ago. And in the last 30 years or so, I have been working together with an international group of people actually trying to further develop a primitive or a very young domain of science called Earth system science, which is trying to understand the Earth as a complex system. And that's what I'm actually here to talk to you about today. And the reason that I went from biological oceanography, which I still do, but what got me moving on in this was that I was appointed to a scientific steering committee in the 1990s for the International Geosphere-Biosphere Program. And I mean, this was like the gods were there. Paul Crutzen, who got a Nobel Prize for figuring out the ozone, sharing it with 2 others, but figuring out what humans were doing to the ozone hole. Bert Bolin, who was the first chair of the IPCC. I mean, really the gods were in the room. And it occurred to me that with my biological oceanography, I was looking at the carbon that was getting caught in biology with the help of the sun in the tiny little plants in the ocean, and going all the way to the fish. And then I stopped worrying about it. And I suddenly realized that, hey, this carbon, I mean, there's something else happens afterwards, and it's all a part of the global carbon cycle, and that becomes the climate, and I was hooked. And so I've been working on it ever since. So, given that we're coming from very different backgrounds, although I have to say, a very good colleague of mine, Mikael Hauschil, is coming to talk to you later this week, I noticed. So you can look forward to that. He's a great guy. I like to start, when it's such a different audience than my usual playmates, with this picture. And I like to start with this picture because I know you've all seen it before. I've been told it's the most downloaded picture from the net. And even though you've all seen it before, I'm willing to bet that none of you have lain awake at night and worried about what it's really showing you. What is it really showing us? Well, it's showing us a couple of things. First of all, it tells us that our ancestors made a terrible, terrible mistake when they called this planet Earth. It should be called ocean. The other thing it's showing you is that there's no umbilical cord. Well, of course, there's no umbilical cord. But what does it mean that there's no umbilical cord? It means 2 things. It means that when we've used the Earth's resources, and make no mistake, it's not money that makes us rich. Nobody can eat money. Nobody can put money on to stay warm. Nobody can live in money. Money has always been a proxy for the Earth's resources. Our ancestors understood that. They bought and sold from each other with naturalia. And then at some point they decided, oh, he doesn't maybe need bread today. Let's give him a proxy he can exchange for bread some other time. That was money. And for a very long time we had a gold standard behind our money to remind us that really, there's supposed to be something behind this stuff. Well, we've taken that away. That was just a complication. But we can't take away the fact that we, like all other organisms, survive by using the Earth's resources. And when we've used all of the Earth's resources, the Earth isn't going to get any more. The other thing that missing umbilical cord means is the fact that we can't really get rid of our waste. Climate's a waste problem. We thought we'd gotten rid of that greenhouse gas waste that was produced when we burned fossil fuels or cut down trees, but it turned out we hadn't. It's in the atmosphere around us, and it's influencing the system as a whole. And actually, I should probably say that even as a biological oceanographer, I'm quite disgusted by the discussion that we're having in the community or in the general public now about plastic in the oceans. We've been throwing out plastic since the 1950s, knowing full well that it isn't, or basically it's non-degradable in nature. That's why we like it. We've had this picture here since the Apollo missions in the late 1960s, beginning of the 1970s, that shows very clearly, there's no pipe that's going to take it away, and 71% of the Earth's surface is covered with ocean. Quite honestly, where did we think the plastic was going to end up? How could it take over 50 years to figure out the plastic was in the ocean? This isn't exactly rocket science. There's another thing. It's the color. This planet looks different than any other planet or any other celestial body that we have in our solar system. We think what's really exciting, we really focus on it all the time, it's climate. Climate, climate, climate. And people say climate is the same thing as sustainability. And, climate, climate. There's nothing at all special about having a climate. Every planet has a climate. It's just a question of how much heat energy do you get from the sun, how much is stored near the surface of the planet, how does it move around, what does it get into contact with. It's the energy balance at the surface of the planet. Every planet has elements left over from the Big Bang. But on most planets or celestial bodies, these are relatively inert. Some people say that Neil Armstrong's footprint can still be seen on the moon. Now, for very good reasons, I don't know if that's true or not. But I do know that if we had a footprint here on Earth from 1969, it would be long gone. And why would it be long gone? Because on Earth, we have life. What makes our planet unique is the fact that there's life. We don't know what life is, but we know what it does. And what it does is it takes some of that energy that's at the surface of the Earth and it moves around elements or combines them in new ways. So it transforms and it transports elements. And every time an organism has been able to get enough free energy out of making a conversion like that, then an organism or an organism group has evolved to do that job. And what this means is for the last about 3.5 billion, nobody knows exactly when life came into the picture, 3.5, 3.8 billion years ago, something along those lines. For the last over 3 billion years, it's been the interaction between what we call the geosphere, which is the energy or climate and all of the elements that we have there, and life that have created the conditions on Earth. And every time something really major has happened in either the biosphere or the geosphere, conditions on Earth have totally changed. Think what happened when photosynthesis evolved. It may have taken a long time for biology to do it, but when they finally did it, instantaneous on geological timescales that we got photosynthesis and produced oxygen in the atmosphere. That made huge changes in the conditions on Earth and caused much of the life that was here to die. Huge. What happened when green plants evolved? Well, suddenly there was a way of getting reactive carbon out of the atmosphere and storing it away from the total change in the climate. What happened when you move around tectonic plates and change the currents in the ocean? Total change in the overall environmental conditions on Earth. 63 million years ago, when a meteor hit the surface of the Earth and changed the energy balance there and did it out with the dinosaurs, total change. So every time we've had a major change in one of these spheres, then we've had a major change in the conditions on Earth. And as I say, it's this interaction between those two spheres that create the conditions on Earth. It's not climate alone. And it is not our politicians when they go to wherever they've just been. This has been going on for 3.8 or 3.5 billion years, that interaction. And what this means, of course, is that the biodiversity crisis is at least as important as the climate crisis. And in fact, it actually worries me more. Why do I say that? I say that because when we get control over our emissions, and I say when because basically we have the technologies we need in order to do it. We aren't willing to because it doesn't fit with our economic system and so on, but we do have the technologies. So when we get control over our emissions, then it'll take thousands of years, so none of us will be here to see it. But the energy balance on Earth will go back to one that isn't impacted by humanity. It may not be exactly the same as it was before we started playing with this, but it will go back to one that is not, it doesn't have a human fingerprint on it. But every time we lose an organism, it's gone forever. So we will never go back to a biosphere that isn't impacted by humanity. Now, in the last 100 or 150 years, a third sphere with the potential to change the conditions on Earth has emerged. And that's, of course, us. We call that the anthroposphere. Anthro coming from the Greek meaning people, the age of people, or man, I think it really is, but people. And that's, of course, what we call the Anthropocene. I'll come back to what the Anthropocene, a little bit about the Anthropocene in a moment, but I know you've all heard of the Anthropocene. And basically, I like to think of the Anthropocene simply as being that understanding of the fact that humanity's activities on Earth are acting as a quasi-geological force, that it can impact the same way that can change the conditions on Earth in the same way that changes in the biosphere and the geosphere can. And if you don't think this is important, think about the fact that when the Earth went from ice ages to non-ice ages, you moved about 80 parts per million CO2 from the atmosphere to the ocean, or the other way around. Took 80,000 years, but you moved 80 parts per million this way, down to here, or up again. Humans, in the last less than 300 years, have moved 137 parts per million CO2 into the atmosphere. 137. Not 80 over 80,000 years, but 137 in less than 300 years. Do you think this system that we're in has come into equilibrium? Absolutely not. And do you think it's going to do it before 2100 when the politicians are doing their modeling and calculating to? Absolutely not. And of course, we see that this human impact is increasing. And as we know that it's increasing, this is actually what the whole sustainability discussion is all about. What do we do about this? How do we manage our relationship with the planet as a whole? Our ancestors, when they stopped running around after their food, their nomadic life, and they traded that for a fast address. I'm pretty sure they started out by dropping their waste wherever it was produced and taking whatever they thought they needed from nature, whether it was game to eat or trees to burn and get energy. And at some point they got to be so many, they looked around and said, hey, this isn't working. This isn't working. We're getting sick from water polluted by our own bodily products. We're running out of game. We're running out of things to... We need to make some rules. We need to manage where we defecate. We need to manage the way we take game. Don't take more than we need. Don't take the pregnant ones. Make sure we use everything we have, and so on. Note, our ancestors, we never solved that problem. We're still managing our relationship with the local environment. As we got to be more, we realized that local management's not enough. If you want clean air and water here in Belgium, then you can't have the Germans and the French and everybody else throwing their rubbish in the air and in the water. So we do regional environmental management. And what the biodiversity and climate crises are telling us now is that we need to manage our relationship for our own sakes, not to save the planet, but for our own sakes, we need to manage our relationship with the planet as a whole. And yet we keep talking about, let's find solutions. We're not going to solve this. We've lost our innocence. We are going to have to manage our relationship with the planet around us, our home, the ecosystem of which we are a part. We're going to have to do that from now on and forevermore for the sake of ourselves and not the sake of the planet. Now, I think it's important to get a little bit of biodiversity in this, even though I was told we're doing biodiversity a different day. So I have two biodiversity slides that I want to feed you. One has to do with the numbers of species and the loss of species. And that's what we usually think of when we talk about biodiversity. And this is the cumulative percent of species in different groups. You've got amphibians, mammals, birds, reptiles, fishes that have disappeared since 1500. And it's really taken off since 1890. Whoa! Some people talk about us being in the 6th mass extinction. We're not. When there's a mass extinction on Earth, you lose between 60 and 90% of life, all organisms on Earth. We're not there yet. But the rate at which they're disappearing is just as fast or faster than it was under other mass extinctions. So if we can't stop this, then we are in a mass extinction. So we usually define biodiversity as numbers of genes, numbers of species, numbers of ecosystems, diversity. And it's desperately important because it is what maintains the resilience in the biosphere. So the biosphere can do its function when it's colder or warmer. You know, the energy balance isn't always the same. So it's really important, all those species that are out there. Maybe not today, but under other energetic or climate conditions, they might be very, very important. So yes, we need to stop the extinction of species. But it's not just about how many species there are. It's also a question about how many they are in relation to each other. Because it's not so important how much you as an individual exchange of greenhouse gases with the world around you. It's your whole ecosystem and what that's doing. And boy, do I promise you, humans have been really, really good at changing the relative abundance of different species. If you could take all of the organisms with a backbone, all the vertebrates on land, and put them on a scale, you would find that about 62% of that, or 65% of the weight comes from our domesticated animals, 32% from us, and less than 3% from wild nature. So we have really been good at changing what's out there, which is why in December, just a year ago now, in Montreal, it was actually the Chinese who were the hosts, but they'd had COVID for so long, the media had been put off so many times that they finally did it in Canada, and the Chinese paid for it. And it was called COP15. COP only stands for Convention of the Parties. It was the COP15 within the Convention on Biological Diversity. And that was at that COP, it was decided that 30% of the Earth's surface, both in the ocean and on land, should be left for nature to do its thing on its own. And in the biodiversity strategy that the EU is currently struggling desperately to adopt, that is also what they're going after, 30% of the area, land and ocean area. And I'm in Belgium right now, and I understand the reason that that they started in the EU, now it's quite a while ago, started demanding that countries made a plan for how they were going to use their marine area, was when they discovered that Belgium had actually given rights to use more marine area than they actually had. So it's going to be a difficult job finding 30% if we can find it. So the bottom line of all this is that when we're thinking about the Earth's resources, I argue that you can use climate and biodiversity as proxies for the Earth's resources, because it is this interaction between climate and biodiversity that have created the conditions on Earth. Now, Earth system science is about understanding how this interaction occurs and what happens. It was first actually defined in, I guess you could say the whole Gaia idea that Lovelock came with, and was a sort of pedagogical way of talking about Earth system science. But it was first presented in scientific language from the Amsterdam Declaration on Global Change in 2001, which says the Earth system behaves as a single self-regulating system comprised of physical, chemical, human, and biological components. And I assume you're going to ask for my slides afterwards, so I've left a little reference in here. A review we did a couple of years ago in Nature, reviews on Earth and environment, which actually gives the history of Earth system science, should anyone be interested. When I started in this game a very, very long time ago, as I say, we could do all the arrows between marine biogeochemistry and the tropospheric chemistry and all these arrows. But we had people out here on the box. We could do all this over here, and then we had people over here as if they were outside the system. We call this the Bretherton diagram. And the point is, the Anthropocene makes us realize humans aren't outside the system. They're a part of the system. And we put together for a book in 2004, we did these now iconic pictures here's 6 examples of things from the socio-economic system. It's population, it's real GDP, global GDP, use of fresh water, use of energy, transport, telecommunication. And you can see there's just been a tremendous increase since the 1950s, which is the stippled line here. So we talk about there being a great acceleration. But if you go over to the Earth system and start looking at things like carbon dioxide in the atmosphere, actually all greenhouse gases do this, temperature at the surface, ocean acidification, tropical forest loss, marine fish capture, nitrogen coming to eutrophication, nitrogen coming, there's total correlation. And you know perfectly well that correlation doesn't prove cause and effect, but in every one of these cases, we do know that the effect happening in the Earth system is because of human activities. So humans are not outside the system, they're a part of the system. And the way we draw the diagram today doesn't have people in a box. It has a box of human population, cultures, values, beliefs. It has our production and consumption. It has our energy. By the way, the only difference between us and all the other organisms out there is, in terms of our impact on the environment at least, is the fact that we have managed to harness external energy. Every other organism it can't transport itself faster than it can run. We can. And so every other organism is limited by how much they can use the Earth's resources. Because we've managed to harness external energy, we have no limits. So we're going to have to give ourselves some limits. And I think there's a growing social appreciation of the fact that humans do have the capability to change the state of the Earth system. When I say state of the Earth system, it means the overall environmental effects on Earth. In 2000, at a meeting in this Biosphere, International Geosphere Biosphere program in Cuernavaca, Mexico. I was actually at this meeting, and there's different working groups are reporting, and oh God, it can be boring when they're going on. And the paleo folk were, they were just going on and on and on and on and on and on and on, and they kept talking about the Holocene, the Holocene, the Holocene, the Holocene, which is the most recent time in the Earth's period in the Earth's history, the last 10 to 12,000 years. And finally, at some point, the vice chair of this scientific advisory committee, who was Paul Crutzen, jumped up and he said, but we're not in the Holocene any longer. We're in the, and you could feel him kind of grasping after a word. And finally he said, we're in the Anthropocene. Gloink. Well, what happened right there? We took a coffee break and went out and talked to Paul a bit and said, hey, that was kind of neat. Couldn't you write that up for the newsletter? Which he did. He found also out that there was a freshwater biologist in Wisconsin, I think, or Michigan. I always get those states mixed up. But anyway, he'd used the term Anthropocene before. So Paul, being the good scientist that he was, went to him, and together they wrote something up for the newsletter. And it made kind of a big splash. And we said, Paul, why don't you try writing that up for Nature? Which he then did. And this is the paper that came in 2002. And a lot of people, I hear people all the time, I even read people write that, the geologists have renamed this period, that they haven't. They haven't. This was a real challenge to the geologists because atmospheric chemists are not allowed to name times in the Earth's history. So the geologists, the stratigraphers who get the honor of naming times in the Earth's history, and who, by the way, have never had to try and name a time in real time, which is giving them real difficulties, made all the proper working groups, and so they're still working their way through the working groups to try and decide what it is they should use. And the idea is that you need to find something, if this is going to be a real period, you need to find something that you can dig anywhere on the planet and find. And this is the golden spike. This is where it actually happens. And there's lots of different candidates they've been looking at. Aluminum, concrete, plastic, fibers, spheroidal carbonaceous particles. The particles we have in the atmosphere, aerosols, and so on. I think actually at the end of the day they've arrived at the radioactive fallout from the testing. But you could also imagine using fossils. Look what's happened to chickens since 1957. We had a wonderful time in my family. We were 4 siblings, and there was nothing better to fight about than the wishbone on the chicken. Because in the first place, there was only one, and there were 4 of us. And one would get it, and then you had to dry it, and then one stood on one side and the other side, and then you pulled it, and the one that got the big side got their wish to come true. But there was another good place where A, 2 people couldn't be a part of it, and B, the third person lost. So this was a wonderful way of entertaining ourselves. You can't even find the wishbone on a chicken nowadays. So we've made tremendous changes. And there's no question, even though the geologists still haven't, and it's very contentious among the geologists whether they should change the name or not, the Anthropocene exists because the Anthropocene is simply the recognition that we are changing the overall state of this planet. But there is also another problem that they're struggling with, the geologists, is that we haven't stopped yet. Right now, the Anthropocene is a transitional stage. We're moving, but we don't know where we're going to. And this is one of the things we come with these models that say, oh, we want to keep it under 2 degrees, but now the models say we're going to be 2.9. Nobody knows where we're going. So even though there's there's a growing understanding or appreciation of the fact that humanity has the potential to change the conditions on Earth, and indeed is changing the conditions on Earth, our ancestors have never met an Earth as warm as this one is, or the amount of greenhouse gas that there is in the atmosphere. This hasn't happened in the last 250 million years, or 250,000 years, sorry, and that's how long our bodies are. We've been here in this particular biological form. So, but in spite of the fact that we're gaining this recognition of the fact that there's a system and we're a part of it, most of our decision making regarding the way we deal with our relationship with the world around us does not yet contain this system thinking. It doesn't respect the fact that human societies operate within the Earth system. Now let's take climate as an example, because that's what everybody does, and it's also something I've been asked to talk about today, so we will do that. And you can see here that, as I say, our ancestors in there, completely like us. I mean, in our present biological form, humans have been here for something like 200 to 250,000 years. But we were hunter-gatherers for a very, 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 very long time, and indeed there were about, they change the number every day, so I don't want to be held to this, but there were about 9 other humanoid species. All of those died out. And our own species was dead lucky to get through the eye of the needle. We know from genetic data that we went down to tens of thousands of reproducing individuals, and that's not very many. So we were dead lucky. Until we get to this period here, the Holocene, the last 10 to 12,000 years, around the last part there, relatively warm and remarkably stable and in temperature. And many anthropologists believe it was this stability that actually gave us the opportunity to begin to thrive. And everything we associate with modern civilization, and now we're talking Stone Age, Bronze Age, Iron Age, written language, Neolithic Revolution, anything you want to relate to modern civilization happened in this period here. And you can say, oh, it's because we managed to figure out how to produce our own food. Not that easy. Because the Aborigines in Australia, although they did eat yams, they never really learned to cultivate, to do agriculture. And yet their numbers increased exponentially in the Holocene until they met Europeans. But that's another story. So everything that we consider to be modern civilization has happened in this period here. And I'll get back to that. What's happening then to climate? In that period there, in that 10 to 12,000 years, the temperature varied by not more than plus minus a half a degree. Plus minus a half a degree. And now the politicians have said, well, it's okay if it's 1.5 to 2. And by the way, we're actually on our way to 3. 2.9, sorry. But let's have a look at what that actually means. You've seen pictures like this before. It's the temperature development in the air since the 1880s when we began measuring temperature. And no, it's not absolute temperature. It's a temperature anomaly where we set 0 is the same thing as the average from 1951 to 1980. And strangely enough, before 1950, it was colder. It's negative numbers. And after 1950, it's going up. Now, this is not a particularly surprising picture because you've seen it before, so I don't want to use very much time on it, but I do want to remind you of one thing, and that is that the cause of climate change is the fact that we've changed the amount, we've increased the amount of heat energy from the sun that we're storing near the surface of the Earth. We are all excited as humans, because we live in the atmosphere, about temperature in the atmosphere. But only about 3%, that order, 3% of the extra heat is stored in the air. Over 90% of it is in the ocean. So if you want to see climate change, come to the ocean. But okay, we like to think about the air. So let's have a look at what this really means. You've seen this picture, so let me show you one that I bet you haven't seen. And this is the temperature on Earth for the last about 2,000 years, where of course you have to get this one by proxies and modeling and so on. And you can see it was gradually getting colder. And when I was a child, scientists were saying a new ice age is on its way. And no, I am not from 1850. But even in the 1960s, you can see it had gone a bit up, but that you couldn't statistically say that the trend had changed at that point. And people my age love to go around and say, when I was a child, they said there's going to be an ice age. And now they say there's going to be those scientists, they don't know what they're talking about. But in fact, you can see you couldn't at that point say that it was a statistical change. Now you can. Now you can say the trend is broken. Instead of getting colder, it's getting warmer. And the rate at which it's getting warmer is much, much faster than it was before. But that's not really very interesting because we know that. What's interesting is where we're going to go. And we can take the projections that the IPCC does, the UN climate panel. We can take the projections that they do. And this is from an older. These are the ones I haven't done it for the newest, but the idea is the same. If you stop your emissions tomorrow, it'll get a little bit warmer, that's the blue line, and then it'll stabilize. If you let it just carry on, it's going to be, the red line going up, and then there are some intermediates. So you can take those projections and you can put them on the figure that I just showed. So that's the figure that I just showed. That's where we are. Where are we going? Yeah, well, where are we going? We can't get out of 1.5 to 2 degrees. And to be perfectly honest, I don't think there's a climate scientist in their right mind that believes 1.5 is still possible. I know they keep coming back from COPs and saying, oh, it's in the respirator, but it's still there. They kind of forgot to say they've turned the respirator off. And why don't they say that? They don't say it because if they did, they'd be looking some of these small island states from the South Pacific deeply in the eye and saying, you're going to disappear and we don't care. That's not really politically a good policy. So we pretend that 1.5 degrees is still there. I think we probably could keep it within 2 degrees if we really, really, really got our acts together. And there wasn't a whole lot that happened last week that convinced me that we've really, really, really got our acts together. Now, if we go here and get up to 4, 5, 6 degrees, most people don't think, or most scientists don't think, that modern civilization as we know it can continue. Why not? Because there will be large areas that will be simply too warm for humans to survive. Did you see what happened in India with the heat waves this year? Because there will be much less area upon which to produce our food. And by the way, the grains upon which we're dependent, when you grow them under warmer conditions, produce less protein and more carbohydrate, so they won't be as nutritious. The plants and animals that are around us, many of them, will disappear. Storms will have much more power, much more destructive power than they have currently. And I can't imagine a situation where we'll be flying. Think of the turbulence out there. No, thank you. And it'll take a really long time before all the ice melts. But if we melt all the ice, and we're talking Greenland, we're talking the West Antarctic sky, or we're talking the ice on Antarctica, we're talking the glaciers. If we melt all those, then we're looking at a sea level rise of between 40 and 60 meters. So this is not going to be, I think anybody in their right mind can say, we don't want to go there. The good news The really good news is that right now, the projections of the IPCC, it wasn't the IPCC, now it's the GAP report from the UNDP, says that we're on a track to 2.9 degrees. And you can say, oh, well, 2.9 degrees, that's phew. It's not 4 or 5 or 6 degrees. That'll, okay. The problem is that we get into this area here, between 2 and 4 degrees of warming. That's where we worry about something called tipping points. Now, everybody's heard of tipping points. What are they? I mean, all systems, complex adaptive systems have tipping points. Your family's a complex adaptive system, and boing, that can change, something can totally change it. So there are tipping points in complex adaptive systems. What are tipping points? It's when, well, let me take it another way. We know for 100% certainty that there are some things that we call tipping elements in this Earth system. Now, those are things that are either there or not there. It can be ice on Greenland. It can be the Amazon, the forest. It can be the current that brings heat up from the Gulf Stream to us. It's not the Gulf Stream, it's the North Atlantic current that brings heat up to us. It can be, ice in the Antarctic as well. Here are several the different examples of different kinds. There's the the green ones that have to do with biology. It's a loss of boreal forest, tropical coral reefs, the Amazon rainforest. The red ones have to do with currents. That can be the North Atlantic current. It can be the jet stream that does strange things, and we suddenly get icy cold weather down here and say, oh, where did global warming go? And if you happen to look at the temperature up in Greenland, you realize that they're shattering all heat records. So we know for certain that in the Earth's history, these things have either been there or not been there. So we call them tipping elements. And when they go from one state to the other, we say it's a tipping point. And we know with 100% certainty that tipping points, at least one of the drivers of tipping points and crossing tipping points is temperature. What we don't know with 100% certainty is at what temperature they actually go. Now, when the IPCC started telling us in 2001 about tipping points, they said, oh, but we don't think they're going to hit until we get to about 5 degrees of warming. And then in their report in 2007, they said, well, maybe 3 degrees of warming. And then in 2013, red, of course, means this is where the risk is high. They said, well, maybe 2 degrees of warming. And in their special report in 2019 about ocean and ice, they said we can't actually put our hands on our hearts and say that we haven't crossed any now. And the really tricky thing about these tipping points is the fact that we talk about them as if one day you'll wake up and read in the headline in the paper, we crossed a tipping point last night. We crossed a tipping point on the Greenland ice cap. No, the Greenland ice cap, after the tipping point is crossed, that is to say we've gotten to a temperature where we simply cannot save the ice. It'll take a long time for it to melt, but we simply can't save it. Then the ice sheet or the ice cap is going to look just like it did yesterday. And just like it's going to in a week's time. And by the way, just like it does right now. Melting very quickly. But we don't know if we've crossed a tipping point. And this is the really dumb thing about them, but there's been some estimates that basically have said, and there was a big tipping point report that came out last week led by Tim Lenton at the meeting. But this is from an earlier study that says, even if we make the Paris Agreement goals, and this is a complicated slide, maybe not for engineers, but most people go into coma, so let me try. And this is the last 20,000 years down here. This is the temperature that we've had. Here's that period, that sweet spot of 10 to 12,000 years that we've really done so well. That's what the IPCC said. The UN panel guys say about where temperature could be going. And the gray bar here, that's the one we're trying to hit. We're trying to keep ourselves under 2 degrees for the Paris Agreement, the COP from Paris in 2019. Even if we make those goals, and absolutely nothing indicates that we will, then there's a risk that we will cross 5 tipping points. I'm not saying it's going to happen, but there is a substantial risk that we could cross these tipping points. That's the West Antarctic ice sheet, the Greenland ice sheet, the Arctic summer sea ice, alpine glaciers, and we're actually pretty sure we're going to lose coral reefs. The good news about losing coral reefs is that as far as we know, there's no feedback to the climate system. In other words, losing coral reefs won't make the Earth warmer. But all of the other ones, if we cross them, will exaggerate, will increase global warming. For example, when you have summer sea ice on the Arctic Ocean, when the sun hits it, the energy gets reflected back into the atmosphere at wavelengths that don't get absorbed by greenhouse gases. So it doesn't contribute to the warming and keeping extra heat at the surface of the Earth. Take away the ice, and the heat goes into the ocean, and I'm desperately looking for a radiator, but the point is, you all know that water is a fantastic place to store heat. So we will increase global warming by losing the ice. And there's a really, really scary thing that happened this year. If you take the temperature for the last 70 years at the surface of the ocean, since the 1970s, you take the temperature, you plot it through the whole year, and you get a line here. And then the next year, you get a line that's very close to, maybe a little bit above, maybe a little bit below. And gradually, since the 1970s, they've been crawling up. But they always overlap each other. So it's kind of like a spaghetti, a bunch of spaghetti you have there. But it's getting up and it's getting warmer until 2023. 2023, the line is just way over the spaghetti. And the really scary thing, nobody understands why. Yes, it's an El Nino year, but there's been El Ninos since 1970s. Yes, there's climate change, but there's been climate change since the 1970s. What's happened in the system that we don't understand that means it's all the way up here now? And does anybody think it's going to come back down there? Where's the heat supposed to go? I mean, it's going to gradually go down, which is a problem in itself because the animals at the bottom are down in the deep cold water are used to like no temperature difference at all because and so you just change it a little bit and they're really stressed by that. So we don't know we don't know whether we maybe already have crossed tipping points. And what worries us, of course, is the fact that the tipping points, the yellow ones here that are expected to go at lower temperatures, if they go, they could do enough extra heating to get the ones that go at a little bit higher temperatures, which would include the current that brings heat up to us from the Gulf Stream, which could then actually get the ones that go at the highest temperatures. You could get a sort of a cascade, a domino effect that and nobody knows if this can happen, but it's happened before in the Earth's history. So it's we need to be respecting the fact that we are part of a system. We are beginning to see political acknowledgement of the fact that we are a part of this system. And why do I say that? Because we've had this picture, this particular one, since 1972, that shows clearly the Earth's resources must be limited. And yet, it wasn't until 2015 that we got a political international agreement that acknowledges the fact that the Earth's resources are limited. And that, of course, was the Sustainable Development Goals. The SDGs, the Sustainable Development Goals, are actually a vision for how we want to share the Earth's limited resources, not only among people, but also other living organisms. Now, people misunderstand these. I've worked with some people in the pharmaceutical industry that came in and said, we want to integrate the SDGs, and number 3 and number 8 are ours. We save lives and we make money and we're darn good at both of those things. I said, yes, that's probably right. 3 and 8 are places where you can make a positive impact. But if you choose 2 where you're good, then find 2 where you're not good and tell me how you're going to be better. I said, oh, but we're not bad at anything. Well, we'll just think about it. And they went back into their working groups, and they came back and said, well, you know, some of the things that we make, they're rather expensive, and this personalized medicine thing that we think is the future, it might not be for everyone. So we might have a challenge with number 10, equity. I said, well, yeah, that sounds right to me, and what could we do about that? And we had a good talk about that. I said, okay, that was one. Now go back to your working groups and find the other one. And they went back to their working groups, and they scratched their necks till they were bloody. And they came back and said, nope, nothing. There's nothing there. I said, oh, that's good. It means you don't produce anything in or package anything in plastic. Oh, we never thought of that. But that's the whole point with the Sustainable Development Goals. There's nothing new on that list. We knew we had challenges in all 17 boxes well before 2015. And in fact, we had UN agreements on women, on peace, on water, on climate, on biodiversity, you name it. So what's new? The new is that we brought all of these challenges into one framework. And then it becomes not the boxes themselves that are interesting. I know it's always there. So choose your box, and you get a picture of yourself with your box. But it's not the boxes that are interesting. It's the interactions between the boxes. And I sat on a group in the UN that wrote the Global Sustainable Development Report in 2019. And we wanted to look at these interactions, but in order to understand the interactions, you had to know how it's going with the individual goals. And what we found out was that for a few of the goals, they were on track to be met. But for some of the others, the trend was in the wrong direction, which means that we're getting farther away from achieving those goals for every day that goes. Now, we did this before the COVID, so some of the numbers have changed, and I'm going to show you newer numbers as well, but I think this is a very pedagogical way that we presented it, so I'm going to do it again here now. The general picture is the same today. There just came a new report here in 2023, but they don't do it as quantitatively as we did. We actually took a deep breath and said, if you believe getting within 5% of the goal is making it, then we don't like dead babies. Child mortality or infant mortality, neonatal mortality, getting children into school, doing really well on those goals. You say, okay, well, what about 10%? Well, then we could actually eradicate extreme poverty, end hunger, get young people and adults reading, get a large percentage of the Earth's population access to toilets and electricity. Wow, this is really going well. Where was it? It was going in the wrong direction. Well, that was over here. That was with respect to malnutrition. 1 out of every 6 people on Earth suffers from malnutrition, and only about a half of them don't get enough to eat. The others get too much or the wrong food, and there's an obesity epidemic over the entire world. It's inequality. We have less than 1% of the Earth's human population owns more than the 50% that are poorest. It's with respect to our absolute material footprint. How much are we taking out of the planet? In our countries, in my country, in your country, if everybody on Earth lived used as many resources as we do, we would need more than 4 planets. And it's only working because we're letting the trend go down for climate and biodiversity, but also because some people aren't getting their fair share. And how long is that going to last? And then, of course, it's climate and biodiversity. And you can say, well, I'm a people person. Oh, I should show you the newest picture first before I go on to that. And that's here. And they did it slightly differently, as I say. They go in and say, where is it we're making fair progress, but we'd like to make it go faster? And it's all the same places. It's all up on the people goals. Those are the lighter colors. The orange and the red say we're standing still or going in the wrong direction. And where do we find that happening? Well, we find it happening with climate and biodiversity, and so it's exactly the same picture that we had before. And you can say, Yeah, but I'm a people person. Let's do the people thing before we worry about the other stuff. And we see it all the time. Oh, we can't do anything about a climate because we've got a finance crisis. We can't do anything about climate because we have a COVID crisis. Ooh, we can't do anything about climate because we have a war in Europe. We can't do anything about climate because we have an energy crisis. So all the time we keep pushing this in front of us. And the reason that doesn't work is that all of the goals that make us rich, and remember, it's not money, it's access to, well, it's food, it's energy, and so on. So the goals that no poverty, getting food, good health, education, water, all of those goals, achieving them comes with costs from the global environmental commons. Remember I said we can use climate and biodiversity as proxies there. And the climate and biodiversity are going like this, and the other ones are going up. But this is a zero-sums game. Basically, you're using the currency that's making this happen down here. And you can party even though your bank account is going down. You just can't party forever. And that's the situation that humanity has brought itself into. And the really observant member of the audience will see, she doesn't have all of the SDGs there. Oh, and by the way, 10 links these. This is the equality thing. How are we going to share those limited resources among, so people can get wealthy? But I don't have all of the goals on here. Why not? Because all of the rest of the goals can be affiliated with or associated with one or more of the 4 tools that society has at its disposal to try and bend the curve. That's what we need to do. We need to bend the curve, so instead of being negative there, it goes flat. And the 4 tools that we have are, yes, technology, but there is no such thing as a sustainable technology. Forget it. A technology on its own cannot be sustainable. It can help us use resources more efficiently, but it's how we use it that tells us whether it contributes to a sustainable transition of society or not. So it's technology. When technology can't solve the problem because technology can't make biodiversity, can't make energy, that's the second law of thermodynamics, can't make the phosphorus that we need in order to grow our food. So technology on its own isn't going to do it. It's how we use technology. So it's our individual and collective behavior. And it's also, we have our economic and finance system and our governance system that we can use to try and get our tools and our behavior to play together. I don't need to explain to you people what the rebound effect is, but think about the fact that about 15 years ago in the EU, the politicians, that is to say the governance level, decided that we were hurting climate too much with our private cars. So they set new standards. Then the engineers came in and they made greener cars. They made more sustainable cars. They drive farther per liter. I don't know what happened here in Belgium, but I know in Denmark we very cleverly at that point put the price of cars down. What do you think that did to our behavior? We buy more and we drive more. And the end result is that we're hurting climate more with our private cars, driving in our private cars, than we were before we got a so-called green or sustainable technology, more sustainable technology. So no technology can be sustainable if you use sustainable as a noun or as an adjective. It doesn't happen. Yeah?
Can you share with us your definition of the rebound effect?
The fact that you can, when you have, well, the best example is always the one with light. In the beginning, we used a tremendous amount of energy and it became more and more efficient, but we started using more and more light because it was more and more efficient. And so the end result is that we don't really get anywhere in terms of using less of the Earth's resources to have light. We just have more light, but we have really gotten some nice green technologies. So-called green technologies. But there's the problem here is that nobody really thinks in terms of SDGs. Can we translate this to the world that we actually live in? Well, yes, of course we can. Because what makes us rich is getting access to energy, food, water, materials for infrastructure and our consumerism. So that's what makes us rich. And all of those activities either take something directly out of the Earth system, those are the green arrows, and it can be we take natural forest and make it to agricultural land, we can take fish, we can take trees, we can take minerals, so those are the green ones, and the black ones are where they put in waste. And these 3 black arrows over here going to the atmosphere, that's climate. But I promise you, if we hadn't discovered by accident in the 1970s that CFCs were destroying the ozone layer, we wouldn't be talking about climate today. We'd have a much larger problem with the ozone layer. Or, God forbid, we had, instead of using chlorine, had used bromine in those chemicals, which would have worked the same way in your refrigerator and your spray, but would have been much more destructive to the ozone layer. Then we dodged a bullet. We totally dodged a bullet. So we still have plastic, and we still have synthetic chemicals, and we still have lots of other things. So climate is kind of a focus at the moment, but it's part of this system understanding that we have to think of. Now, the interesting thing is that politicians are between us and those processes there. Those are mostly the infrastructure for getting energy, getting consumer products, getting food. Those are mostly private companies. So the private companies are sitting with their hands on the lever. They can decide how big that arrow is going to be, both the black and the green ones. Now, obviously, they need politicians and the economic system to help them do the right thing, as it were. It should cost like crazy to produce waste. Nature doesn't produce waste. It should cost like crazy. But we're having a hard time getting a CO2 price, but it's coming. But it's not just about CO2, it's about all of our waste. So what we need to be doing is focusing on those arrows, and we need to be thinking about cost efficiency. I translated this badly, sorry. Cost efficiency into all sectors. And you say, well, I know about cost efficiency, but you've always thought of cost efficiency in terms of money. None of you would use more money than absolutely necessary to buy a good or a service, but you all use more resources than are necessary to maintain the lifestyle you have. I'm not talking about even changing that at this point. I'm just talking about using our resources as efficiently as possible. So we need to be focusing on these arrows, and our goal must be to maximize the human welfare. At the same time, we minimize the environmental and social costs. This should also say social costs here. So, we know that continued societal development requires that our resource demand mustn't exceed the supply. And I've already said there's like we'd need over 4 Earths if everybody used resources as we do. That's in fact the environmental. If you think about Brundtland, if you Google sustainability, you'll get the Brundtland report from 1987, and it was fantastic in the sense that it said, hey, sustainability isn't just about the economic bottom line. There's also an environmental and a social component. And at that point, they couldn't define what the environmental and social components were. But the environmental component is that we don't use more of the resources, that our demand doesn't exceed the supply. The social part is how do we share those resources. But we know we can't use more than the supply. And if you think about how do we quantify that supply, how do we know how much is too much? And we have our politicians, when it comes to climate, that say, oh, we can't let human-caused global warming be more than 1.5 to 2 degrees. Well, it's rather simple, actually. Even I can do it, and I know all of you could, is to go back to your desks and calculate how big is the garbage dump. How big is the garbage dump for greenhouse gases in the atmosphere that we share with every other person on this earth? So we know how big the supply is. That's the size of the garbage dump. And we also know it's more than half filled. And we know exactly who filled the first half. So the whole discussion, the whole political discussion, is about who gets the right to use the second half. But that's just climate. What about all these other resources? It's not only climate we're impacting at the global level. And that's where the idea of planetary boundaries comes in. Now, what are planetary boundaries? We're used to the idea that ecosystem, well, no, first, the system you know best, that's your body. And if you break your leg, then the doctor can probably get it working again, and you might or might not limp. Might be there's no limp at all, but whatever, it's never going to be as strong as it was before. There's a state change in that system. We know with ecosystems, if you have a lake, a clear-watered lake, and where the lake gets down to the bottom and you have bottom plants growing there, and then you throw in nutrients, the water gets all murky, and light doesn't get to the bottom, and the bottom plants die. Now let's take away the nutrients. Do the bottom plants come back? No. Where should they come from? The water's all murky now. You've had a state change in that ecosystem. And we know that from lots of different ecosystems. We can go in coral reefs, we can go from coral dominance to algal dominance. Here's the clear water to the turbid water I just spoke of, grassland to shrubland. And that can happen for completely natural reasons, nothing to do with us. But it can also happen because of things we do. So we accept the fact that when you're talking ecosystems, that either nature or humans can change the system. Now, does the Earth have different states? Well, we've already talked about the fact. Of course it does. Here's our the last 100,000 years. It's actually, this is just temperature over Greenland coming from ice cores from Greenland. But when temperature was changing over Greenland, it was changing other places as well. So this isn't global. It's just over Greenland. And here you have this period of grace, this the humanities, the Holocene, the period in which we've. And so what we said was, okay, we know for certain that our species can thrive under these conditions here. We don't know for certain that we can thrive under other conditions. It certainly didn't go very well for our ancestors in this period here. So the precautionary principle says it would be very unwise, indeed foolish, of humanity to knowingly do something that could change the state of the Earth system. In other words, change the overall conditions on Earth. So we said, okay, what are the important things that are maintaining, well, the most important, of course, maintaining the Earth in the condition that it is right now. And the most important, of course, is that the Earth has an unusually circular orbit around the sun at the moment. And you can say, well, that could change tomorrow, so why should I worry about this? But there are some very boring scientist types that devote their lives to trying to understand what's going to happen to the circulation, the orbit of the Earth around the sun. And they say, oh, no, this will continue for thousands of years. So there's no reason to believe that the state of the Earth system should change unless we do something to change it. So we went and said, well, what are we doing? What are the important processes on Earth that we are changing that could potentially change the conditions on Earth? And we found 9. The most important of these are, of course, climate change and life. Biosphere integrity and climate change, or the geosphere and the biosphere. We've talked about it in different ways, but this interaction between climate and biodiversity. But there are lots of other things that we're doing and impacting the Earth at the global level that would operate through either the biosphere, biodiversity, or climate, or both. And that's the release of reactive nitrogen and phosphorus to the environment. People tend to think that, oh, this is just a local problem. Well, we used to think that what came out of a chimney was just a local problem as well. But in fact, especially the nitrogen cycle, the nitrogen cycle, when you get extra nitrogen, you create greenhouse gases, nitrous oxide, so you have a climate effect. You can also, with the phosphorus, have an oxygen effect in fresh water, which then affects the biodiversity and so on. And actually, you can have it in the ocean as well. Land system change. There's lots of ways we change land system, but the most important in terms of the state of the earth and that could change the state of the earth, that's forest. Because forest not only captures reactive carbon and keeps it so it's got a sink for carbon, but it also changes the albedo. So that when you take the forest away, the earth keeps more warm. So it changes the radiative forcing on Earth. Novel entities. What are novel entities? Novel entities are ones that wouldn't be found. They're things that wouldn't be found on Earth if humans weren't here. It's synthetic chemicals. It's gene-modified organisms. It's plastic. Things that wouldn't be here if humans hadn't been here. Freshwater change. How much water are we taking not only out of aquifers but out of soils when we drain, and then we get carbon coming out from areas that have been covered by water. It's ocean acidification, because when we put more CO2 into the atmosphere, if you think all the way back to 4th grade chemistry now, hang on to your hat and glasses, when you increase the partial pressure of a gas on one side of a membrane, in this case the surface of the ocean, what happens on the other side? It increases. And what happens when you put CO2 into water? You get carbonic acid. And the ocean surface has not been more acidic for the last 23 million years than it is today. Now, obviously, we weren't measuring acidity 23 million years ago, but we do have proxies where we can go in and look at it. Now, of course, it's still, it's not dangerous for us. It's still higher pH than your shampoo. But there are very many organisms in the ocean that create calcium carbonate, not least of which corals. But it's not just corals, it's also oysters. Oyster farming on the west coast of the United States is challenged at the moment because baby oysters have paper-thin calcium carbonate shells, and they don't like it when it gets to be acidic. It's particles in the atmosphere. Big volcanic explosions, they end up cooling the earth because of the particles, so you do have effects there. And the most important thing is that we're changing the balance. There's more, if we change the ratio of the clearness of the air in the northern and southern hemisphere, we start pushing around where the monsoons are happening. And I have to tell you, people that live with monsoons don't like it when they aren't there. And did we get all the way around? Oh yeah, of course, the ozone hole. So, or the hopefully lack of an ozone hole. So we call the climate and biodiversity or biosphere integrity boundaries as core boundaries, and all of the other boundaries actually operate through either climate or biodiversity or both. We first introduced the concept of the planetary boundaries in 2009, and then we did it with 2 papers, one in Nature and one in Ecology and Society, and then we did an update in 2015, and the most recent came in September this year. I was the lead author. I have to tell you, 29 authors, 3 years of work, and I got to be 10 years older in that time. Not to mention the fact that my dear friend and number 2 author decided to die in the middle of the process, and that didn't make life any easier. So it was almost like writing a GSDR report, I have to say. But the interesting thing is that paper, that update we had in 2015, has now been downloaded almost 300,000 times. The paper that came on the 13th of September has been downloaded 275,000 times. It took 8 years for the 2015 paper to reach 300,000, and it's taken us 8 weeks to make 275,000. That tells me this is a discussion that is beginning to ripen in a very big way in our society. So what did we find out? Well, First of all, let me tell you that when we do the planetary boundaries, we try and use the best scientific evidence to say, okay, how far do we think we could push these without raising major, making a major risk that we change the conditions, or we trigger something that changes the conditions on Earth. And we set a planetary boundary. Now, the planetary boundary on this picture for each of them is at the outer ring of this green circle. And if you can keep yourself in the green circle, then you're in a safe operating space. Planetary boundaries must not be confused with tipping points or thresholds. They are not. They're more like blood pressure. If your blood pressure is over 120 over 80, it's not a guarantee you're going to have a heart attack or a stroke, but it does increase the risk, so we try and bring it down. And many people misunderstand that about the planetary boundaries. But if they're going to be useful in terms of developing a way of managing our relationship to the global environment, they can't be all the way out at the edge where you say, okay, here we know it's going to be. So they're deliberately conservative. But you can see we're on the wrong side for 6 of the 9. That doesn't worry me very much, because in the 1990s, we were either on the wrong side or very nearly on the wrong side for the stratospheric ozone depletion. And now, thanks to international negotiation and the banning of CFCs, we've now brought ourselves well back into a safe operating space. What scares me? That's the fact that when we did our update in 2015, the 4 we found were on the wrong side of the boundary are all further transgressed today than they were then. What this means is that the pressure on all of these processes in the Earth system is increasing as we stand here and look at each other. And any one of these on their own, it doesn't take much imagination to realize that any one of these on their own could bring the Earth into entirely different condition that was less suited for humanity or humanity's evolution. Another interesting thing is that 3 of these, the biosphere integrity, which is the biodiversity, land system change, which is where we use felling of forest, and freshwater change, where we're using fresh water from aquifers and from the ground, that they all represent things we're taking out of the Earth system. The other 6 relate to waste. Greenhouse gas waste, pollution of synthetic chemicals, particles in the atmosphere, CFCs, and so on. Nature, in its 3.5 billion years, has done away with waste, which is how it's managed to survive with limited resources on Earth for the last 3.5 billion years. Don't even dream of humanity with its use and throw out culture can think about being here for 3.5 billion years. No way. So what we need to do is to reduce, preferably eliminate our waste, and that needs to be a focus area. So what's new about these? Well, first of all, this is the first time that we've defined all the boundaries. And I said there were only 4 that were transgressed in 2015. That's because we didn't have them all at that point. We've also come with new metrics for water, where we include not only how much water you're taking out of aquifers, that is to say the blue water, but also how much we're taking out of soil, which is the green water. But most importantly, and something I'd like to use a little time on, is this biodiversity one. I told you in the beginning, having the number of species that you have, or genes or whatever, is important because that's what gives the biosphere its resilience to survive under different climate conditions. So we have a metric here called genetic, and it's the rate of extinctions. And of course, we can't get things back. It's the rate of extinctions. We have to bring it into the natural rate of extinction. And right now, we're something between 100 and 1,000 times higher than the natural rate of extinction, thanks to our activities. But we also need something that captures the functionality, this moving around of elements and energy. What can we use there? We took a thermodynamic approach and we said, okay, we all learned in primary school that the energy that feeds nature, all ecosystems, a few minor exceptions at the bottom of the ocean with chemolithotrophs, but basically it's photosynthesis. Photosynthesis feeds nature. So we calculated how much photosynthesis was there every year in the 10,000 years before the Industrial Revolution. Turns out it was very stable. Not surprising, because the conditions were so stable in that period. So it was very stable. It also turns out humans are using about a third of it. 30% we're taking out, either by changing natural photosynthesis to our fields for food, or by biomass, or putting infrastructure on places where nature should have been. That's 30% of the energy that nature had available to it that it doesn't have any longer. That has to be a driver of biodiversity loss. And that means that we can use either land area or biomass use as a metric for effects for human effects or business effects or whatever on biodiversity. It also means we say that this is too high now. We have to bring it down. So we can't use that 30%. But we're like every other organism. We need photosynthetic products. So it tells us where we need to do innovation. We need to do innovation there where we can make photosynthetic products someplace where nature wouldn't have thought of doing it. Bioreactors at the surface of the ocean, on roofs, I don't know. And instead of focusing on capturing carbon and burying it, which is use and throw out, we should be focusing on capturing carbon in products, in photosynthetic products that we can refine and use. And we shouldn't be burning the damn stuff either. I mean, there's lots of value in photosynthetic products. And so we should really be focusing on this biorefining, on making photosynthesis happen where it wouldn't normally have happened. We did some other modeling in this study where we actually showed that when we modeled interactions between deforestation and climate, it's basically going to be impossible, very unlikely, probably impossible to meet the Paris goals unless we respect a limit for deforestation. At the moment, deforestation is increasing, that is to say, less forest area everywhere on Earth except one region, China. Everywhere else, forest area is decreasing. Why do we say that it'll be very difficult? Well, look at this. This is a little complicated, but I'll walk you through it, and most of you guys model anyway, so you can do it. We model at 3 different scenarios. 350 ppm CO2 in the atmosphere, 450 ppm, and 550 ppm. And then we say, okay, we have different degrees of forest cover. We have the green, which is if we stayed within the planetary boundary, which we actually left in about 1988. We have it where we at the upper end of the zone of increasing risk, which would be 60% of the boreal and the tropical forest left and 30% of the temperate. And then we go beyond that and we say, okay, 40, 20, 40. And we say, okay, at 350, if we'd kept the forest area as it was in 1988, at 350, then you would have a source of carbon from the forest. And we do 2 time periods because everybody works with 2100, but I promise you, biology is not going to be in balance by 2100. So we run the models until they get into balance, and we find that you have this increasing. So if it were 350, then we would have a source, a source of something about 70, 75 gigatons, something like that, of carbon. But we don't have 350. We're already up at 420. So we're approaching 450, and that, of course, means that at 450 there's a fertilization effect, and so we can see that if we way exceed the felling of forest, we come up to over 200 gigatons of carbon that we lose in the sink. And at 550, because of the fertilization effect, it goes back. But had we stayed at the same level as the 1988 forests, we would have a sink of 150 gigatons of carbon in the forest. So we're looking at a difference at 450, which is what we're about to get up to. We're looking at a difference of 350 gigatons of carbon that are controlled by how much we deforest. And I don't know about you, but in Denmark we have a law on climate which says our major goal is to reduce CO2 emission to the atmosphere. And in the very first paragraph, it has a number of guiding principles. And the guiding principle, I can't remember them all, but you'll get the idea when I say it should be as cheap as possible. It shouldn't cost jobs. Shouldn't make Danish companies move out of the country. It shouldn't mean that we don't have healthy economic public finances. It shouldn't turn the poorest people. Shouldn't hurt them more than. I mean, you can see where they came from. The finance ministry was in fine form that day. Nowhere in that law does it mention nature. And yet, over half of our so-called green energy is burning biomass. So we cannot look at climate without looking at nature. We did the same thing in the ocean. We've got the 350, 450, and 550. Not surprisingly, CO2 accumulates in the surface of the ocean at these. Not surprisingly, because you're changing the partial pressure above, and so you're getting more down here. It's not just that reason, though. The other reason is that bacteria are more active in a warmer environment, so they're pumping out more CO2 at the surface, which is fine. I mean, this is helping us really a lot now in the models. But our aim, it's going to continue as long as we keep putting more CO2 in the atmosphere. But our aim in all this is to stabilize the CO2 in the atmosphere and then to reduce it. Keep talking about we're going to do DAC. I have my doubts, but some people believe in direct air capture. If we reduce the CO2 concentration in the atmosphere, what do you think is going to happen to the CO2 in the surface of the ocean? And there's about 50 times more carbon in the ocean than there is in the atmosphere. So it's going to take a very long time to be able to get that to. But we don't talk about that very much when we talk about doing DACA, whatever we're doing. Another interesting thing about this part of the modeling is this. We look at how much material, photosynthetic material that's made in the surface layer, how much falls into the area just before, just under the light. And this is probably the largest ecosystem biome in the world. Whales go down there to eat, and they're like, how much is it going to change? And what the models tell us is that there's going to be a loss of about 3% in the amount of material coming down. But you can also do those estimates on the basis of empirical data, where we go around in the ocean and we measure. This is where it helps to be a biological oceanographer. You can go out and measure what happens in warm water, what happens in cold water, what happens in. So we have some relationships that we've worked out empirically. If we apply them, wow, by gory, it seems like about 10% less coming down. Now, there's no other food source for the organisms in this ecosystem. And if we change the amount coming down to them by 10%, that's going to be huge. It's not something we talk about, but it is something that paleo models suggest has actually happened in the past. But what this big difference between the modeled and the empirically derived estimates does is it reminds us of the fact that in the models being used by the IPCC right now, biology is only very primitively constrained. In fact, the models that were used for the AR6 don't even agree as to the direction of change for primary production in the ocean in the face of climate change. Will there be more or will there be less? And one of the most important biological signals in terms of climate change has been, historically, in the Earth's history, the photosynthesis happening in the ocean. And we don't even know whether there's going to be an increase or a decrease according to the models. And there's a lot of other biological things that aren't very well constrained in these models. We've kind of been operating, and I guess you guys have probably been trained in this thinking that, you know, it's physics that decides and biology rides on the back of physics. But remember, for 3.5 billion years or so, it's been the interaction between biology and physics that have created the conditions on Earth. So we really need to be working on better constraining the biological interaction, biological-physical interactions here. So the take-home messages from our newest Planetary Boundaries work here are, one, the pressure on critical Earth system processes is increasing as we speak. And in fact, none of the planetary boundaries are set at the level that they were in the Holocene. They're all higher. So we are experiencing, on all of these points, we're experiencing a world that none of our ancestors have. And all of the planetary boundaries that we establish, we're not saying, oh, let's go back to the way it was. No. There's lots of scientific evidence that there's a certain robustness in the system itself. And we're trying to capture that robustness because we're also trying to be realistic on this. It's not enough to focus on climate alone. It's interactions in the system that are really important. We need models that better capture the interactions between the biosphere and the geosphere. And we're already using too much biomass. And we keep talking about we're going to have a bioeconomy and we're going to replace all these fossil fuels with bio, which I think we probably will. But what that means is we need to think innovatively. We need to create photosynthesis where it wouldn't naturally occur, or more of it where it does naturally occur. And make no mistake, just because we can harvest more from agricultural land than we can from natural forest to eat, doesn't mean there's more photosynthesis in agricultural land. Quite the contrary, there's usually less. And I also think we need to institutionalize, maybe not exactly this framework, but something like it. Because we can't continue to manage, and I'm sure your laws in Belgium will just look like our laws, and certainly in the UN, we have a convention for biology or biological diversity over here, we have a convention for climate over there, and we have any number of pollution conventions up there. And we don't have anything that looks at the interactions between these. And you hear people and politicians saying, oh, well, there's a conflict between climate and biodiversity because no, sustainable development isn't a place or a state or a thing. It's a process. It's a process whereby the value that we get out of using the Earth's resources comes with a minimum of social and environmental costs. And that means sustainable development is all about compromising. And sometimes it's important that you don't remove biodiversity to have a windmill. Other times, it's probably okay. And our laws don't work that way. Our laws say if there's a three-toed sloth here, you can't do anything. Well, sometimes maybe you should be able to and do something better for the three-toed sloth over there. But not every time. And we need to figure out how to deal with this kind of uncertainty and making these kinds of compromises in our society. So the Planetary Boundaries framework attempts to identify a safe operating space for human perturbation of the global biophysical processes, the ecosystem upon which we depend. And we've actually got a paper that's just been accepted. It hasn't come out yet in the proceedings of the National Academy of Sciences that argues for, until now when we think about global commons, we're thinking about what are we going to do with the resources in areas that aren't under national jurisdiction? Who's going to get them? or maybe nobody's going to get them, like in the Antarctic. But it isn't just about resources. It's also about protecting the processes that keep the Earth system in the condition that it's in and that we know our species can thrive in. So we're talking about planetary commons as well. Some of you may have heard of Kate Raworth and donut economics, and what she does is she takes this, the planetary boundaries, and says this is the same thing as environmental sustainability, or this environmental component of sustainability, and then she has an inner circle, which is minimum human rights, or how we share the Earth's resources, which is representing the social sustainability, or the social component of sustainability. And what she gets out of it is a ring, or a donut, she calls it. And she calls it donut economics, because the space where you can operate is within the donut itself. The sustainability challenge then becomes developing tools and mechanisms to share the Earth's limited resources among 9 to 10 billion people. And we will be 9 to 10 billion people. And don't tell me that it's a good idea to distribute condoms in Africa. Yes, it's a wonderful idea, because I think women should have rights to their own bodies. But it isn't going to solve the problem, because right now, there are 2.3 children being born for every woman on Earth. That's almost replacement. 2.15 would be replacement. So we're almost down at replacement in terms of fertility. And yet, the population continues to increase. Why? Because some of us aren't willing to respect our expiration dates. We're living so much longer. When I was born, the age distribution on Earth looked like a Christmas tree. Lots of people got born, and then they immediately started dying. We didn't like that. We've really been successful in stopping infant mortality. And so now it looks more like a box, except in some countries it looks more like an upside-down triangle. So we will be 9 to 10 billion people, and we have to figure out how we can feed, clothe, transport, and maintain 9 to 10 billion people without ruining the planet that we're on. And I'm willing to bet, if you go home to your families and say, what do you think of sustainable development? Or the guys who aren't here now, and you go, what do you think of sustainable development? You won't find anybody that says anything negative. I mean, who would say anything bad about sustainable development? That would be like a no-no. So they're not going to say anything bad. But most of them will continue, in their own minds at least, and say, but I'm glad somebody else is worrying about it so I don't have to. What could be more important than sustainable development? Who is it that doesn't want their children to have a better life than them? I mean, maybe not in material sense, but better health, better time with the family, and so on. And certainly there are an awful lot of people on Earth that need material development as well. So development, that's a no-brainer. Sustainable, that just means it can continue as far out as the eye can see. And as long as the bank account, as long as the balance on the bank account is on its way down, we know this can't continue as far out as the eye can see. So sustainable development is not a nice to have, it's a need to have. And somehow we have to change the narrative and the story around this. I have, for all of my sins, been doing a good deal of consultancy with I wouldn't call it consultancy because I haven't been paid for it, but I've been talking a lot with industrial organizations and companies and so on. And in that connection, I was really lucky enough to meet John Elkington, who was the guy who figured out, found the triple bottom line something like almost 30 years ago. And he's completely enamored of the Sustainable Development Goals. He calls them a purchase order from the future. I think that's really neat. A purchase order from the future. And we all have a responsibility when it comes to delivering on that order. And that's not the way we usually think as scientists. Have you ever really worried about what I'm doing? Could it contribute to a societal transformation. Doesn't mean that I think everybody should be doing something that all research has to be. But there's so much of what we're doing where it could contribute and we're not bringing it out. We have this idea, we're talking about solutions. The whole narrative is wrong. Complex adaptive systems like the Earth system don't change with quantum steps usually. Okay, a meteor can hit it and do it. But basically, they change with many small steps. And this idea of we're waiting for the magic solution, which will probably be technological and mean we don't have to do anything ourselves, is just not going to happen. When you change a system, you do it with lots of small steps. And if your family's dysfunctional, I mean, that's a complex system as well. If it's dysfunctional, you don't change it in one big step. You do lots of small things. And we need to be looking at how our research can contribute, or is our research pushing things in the wrong direction? So I think the Sustainable Development Goals can be used as a compass for achieving sustainable development, exactly because they force us to acknowledge that we are part of an ecosystem. And we're not only a part of that ecosystem, we're entirely dependent upon it. Thank you.